To plan ahead, an AI agent needs an imagination, a world model, a learned simulator of how its environment will change when it acts. But these simulators face a brutal tension. To stay accurate over a long-imagined future, they need deep computation. Yet deeper models are expensive and tend to spiral into error. This paper resolves that tension with a surprisingly elegant trick. Just loop. First, what's a world model? It's a network that learns the rules of an environment, so the agent can dream forward, rolling out hundreds of imagined future steps without touching the real world. That makes learning dramatically more sample efficient, and it's a cornerstone of modern reinforcement learning and embodied AI. But here's the core problem. Faithful long-horizon simulation needs deep computation, because physics unfolds by applying the same laws over and over. Yet a fixed-depth model spends the same effort on every step, and two failure modes bite. Small errors compound into garbage over long rollouts, and just making the model deeper blows up the parameter count and inference cost. The insight is borrowed from loop transformers. Instead of stacking many distinct layers, you take one shared transformer block and apply it again and again to the same latent state. Crucially, the depth of computation is now decoupled from the parameter count. You can think harder without carrying more weights. And looping is a beautiful match for world modeling specifically. Physical dynamics are an iterative process. A state evolves by repeatedly applying roughly the same transition law. So modeling a single step as repeated applications of one shared update operator mirrors the structure of reality itself. The architecture echoes the physics. Here's the full framework. An encoder turns the observation and action into a latent. Then the heart of the model, the looped dynamics core, refines that latent through repeated iterations of one shared block. Lightweight heads decode the next observation, reward, and a done flag. And on the right, the two payoffs: huge parameter efficiency and stable long rollouts. Dynamics core has three parts, a design they call prelude-recurrent-coda. The prelude prepares the conditioning signal. The recurrent block is the shared transformer, looped t times. This is where the iterative refinement happens. And the coda does one final, separate projection to produce the next state. But looping the same block hundreds of times is dangerous. The latent state could blow up to infinity. Their fix is a spectral stability constraint. They parameterize the state retention matrix, so its eigenvalues are mathematically forced to stay between 0 and 1, making it contractive. That guarantees the latent stays bounded no matter how long the rollout, by construction with no tuning. Looping unlocks a second superpower, adaptive computation. Not every moment of physics is equally hard. A ball in free flight is trivial, a multi-body collision is not. Because the model can simply halt the loop early, it spends few iterations on easy transitions and many on hard ones, matching effort to difficulty automatically. To make this robust, they train with variable depth. Each training example samples its loop count from a Poisson distribution, so the model learns to produce good answers at many different depths. That's what lets it flexibly trade compute for quality at test time, just by dialing the number of loops up or down. One more clever piece: deferred decoding. During a long imagined rollout, you don't decode a full image at every step. That's wasteful. Instead, the model keeps reasoning purely in the compact latent space, step after step, and only decodes back into observations at the very end. All the thinking stays cheap and abstract. And the payoffs are exactly what the theory promised. On the top right, parameter efficiency. Loop WM matches much larger baselines with up to 100 times fewer parameters. On the bottom, stability. Where a normal world model's error explodes over a long horizon, the spectrally stabilized loop WM stays flat and reliable. That 100x efficiency is the headline. Because long rollouts run the dynamics model thousands of times in sequence, every saved parameter compounds across every step. A model that matches a giant network at a fraction of the size is enormously cheaper to actually deploy, the whole point of a world model you can run in real time. They tested on text-based simulation benchmarks, Science World and Alf World, predicting how the world changes after a sequence of actions. Their roughly 1 billion parameter loop WM beats Claude Opus, a model over 100 times larger, by 21 points on exact match for Science World. Tiny model, frontier-level world modeling. The bigger idea is the one to remember. We usually scale AI two ways: bigger models or more data. This paper proposes a third, orthogonal axis, Iterative latent depth. Keep the model small and the data fixed, and just loop more to think harder. Genuinely new scaling knob for world simulation. A few caveats worth flagging. The link between the inner loop and real physical time is conceptual, not exact. The loop refines a latent estimate. It doesn't literally tick out seconds. Headline 100x efficiency is a best case that depends on how the difficulty of transitions is distributed. And this is an early, foundational exploration, rather than a fully battle-tested system. So here's the one-line takeaway. Instead of building a deeper, heavier simulator, build a small one that loops, refining its picture of the world over and over, thinking longer on the hard moments and staying provably stable the whole way. Same imagination, a fraction of the size. Thanks for watching.